Okay. So this lecture we will just finish up on dry docking, and then we will go into something known as bilging, which is, we will come to that. So let's there are a couple of more problems and some more sections on this dry docking. For instance, let's finish this problem. Okay. Now you are told that there is a vessel which is going to be dry docked, and it has the following conditions. Its draft forward is 7.92, draft aft is 9.3 meters, and km0 is 11.43, kg0 is 10.90, mctc is given, tpc is given, lcf is so much forward of ap, length is given, displacement is given. Now in the dock, the depth of water initially is 10 meter. Find the effective GM of the vessel after the water level has fallen by 1.2 meter in the dock. Okay. So water level has fallen by 1.2 meter, and then you are asked a final draft. That is the question. Okay. Now the only slightly thing which you might not think of in this problem, the other thing is very much similar to our previous problems, like you find the G0, G1 change in GM, and you have to find the final GM in this case also. So there is only one. Okay, first of all, you are given that the draft forward and aft are given, so you know the initial trim. Okay. Then okay, let's see this. You are told that the depth is 10 meter, and let's take the aft section. Okay. Because why do we take the aft section? It's because aft is deeper, means aft the draft is more. It's always like that, and in this case also it's like that. So it's 9.3 meters. Therefore, what do we see? We see that there is a 0.7 meter clearance. Now the only mistake that will come, it comes obviously when you look at this, when you do this problem, will come is you are told that, see, the water level has fallen by 1.2 meter in the dock. Now one thing you might directly do, for instance, is that the change in draft in that in the aft position, how much would you consider it? You might think, see, initially the depth is 10 meter and this is 9.3 meter. Now so this is 10 meter and the ship, this draft is 9.3, there is 0.7 here. Now if you here some 1.2, it's dropped down by 1.2 meter. Now the first direct way of thinking would be that you will suddenly think this 9.3 has dropped down by 1.2, therefore it will become something 8.1 it will become. You understand what I am saying? But it does not fall like that. You understood the that in the dock the water level is falling down. Okay, you understood what I am saying? It's a dry dock. So what has happened? There is water in it. That is how a dry dock operates. So initially there is water, and what is done is they have some ballast, and they are removing the water. They have forced the water out, and water level is falling. So directly you might think that, let's say if it is 9.3 initially, the draft will become 9.3 minus 1.2. Okay, but think of it. See, what will happen is, actually when the water level falls, actually the ship will come down. Okay, you understood that? So it will come down, and this aft will hit the ground. Once it hits the ground, then that is true, whatever is remaining it will fall down. Therefore this 0.7 it will just come down just like that, right? Therefore when it is at that time also draft is 9.3, it comes down like this, its draft is still 9.3, it will come down and hit the ground, and then it will decrease by whatever is left, 1.2 minus 0.7, 0.5 it will decrease. In fact, that is only slightly thing which you won't think of. other than that, then the problem is straightforward. Okay, so now we have this clearance of 0.75. Now therefore we can say that the change of draft aft is equal to what? It's equal to 1.2 minus 0.7, it's equal to 0.5. So instead of just saying it's 1.2 meters, it actually is 0.5 meters. That is only trick in this problem. So now you know that when you have a ship sinking, or trimming totally, the total change of draft is given by change of draft aft. There is a formula. It is the sum total of the sinkage plus trim. Okay, that is the total change of draft. So okay, just remember some formulas, like you can go one by one. Like first you have to remember this thing, change, that's trim is equal to moment divided by MCTC. Okay, that moment producing trim divided by MCTC will give you the trim. Then change of trim aft will be small l by capital L into that, okay, into T. That will give you the change of trim aft. Now the change of draft aft will be this plus that weight by TPC. Okay, just know what are the signs, that's all. Means if it is a weight added, if it is a weight removed, you have to make it plus or negative, that you can think of, you can. So the total change of draft aft is in this case P by TPC plus remember the trim itself is given by P into L by MCTC, and therefore the change of trim aft will be L by L into that. So this is the expression for the change of draft aft due to change of trim aft. Like there are a couple of things now. There is a trim, there is a trim aft, then there is a parallel sinkage, there is a change of draft aft. Okay, trim draft change of draft is a final thing, which is sum total of the change in trim plus sinkage. Yes. Okay, so this will give you the change in draft aft. Now we know the change in draft aft, it is given as 0.5 meter, we have already calculated it. So if you do that 0.5, you put this P, you know TPC, so TPC is known, then L is the distance of the center of flotation, that is also given, length of the ship is given, P we do not know, again L is the length of the center of flotation, MCTC is given. So MCTC you know, L you know, L you know. So in this you solve for P, okay, you will get P as some 358.2 tons. This gives you the reaction force from the when it touches the ground. Now the rest is actually very straightforward, that is you can have you are asked to find your final GM, that is final GM is always got by initial G0 M0 minus G0 G1. Okay, this will give you your final GM. Now G0 M0 you will get by K M0 minus KG0, or is it the other way around, KG0 KM0 minus KG0. Okay, that will give you your GM0, the G0 M0 minus G0 G1. Now this you have the data, KM0 is given, KG0 is given, so that is straightforward. Now G0 G1 there is a formula, we have already derived it. Here G0 G1 is the change in the G, or the change in the metacentric height, that is P into P you have just calculated, KG0 is known, W is the displacement of the ship, P is known, so we know everything. So you calculate G0 G1, and once you know this, you get your final, this G0 M0, this is your G1 M0, which is your final GM. This is one of the questions of the problem. This is one question. Then how can you find the if you are asked to find the final draft is always found by, first you have to do, when the final draft is asked, you have to find the bodily sinkage first. And bodily sinkage, then you find the change of trim, then you find the change of trim aft, change of trim forward, then you find that change of trim you add to the initial trim in the forward and backward direct, in the aft and the forward. It's always, this method is always fixed. Okay, when you are asked to find the final drafts, this is the method. I'll just write it down. First find the bodily sinkage, 2 you find the change of trim. Change of trim is always the moment causing trim divided by MCTC, that changes according to the problem, moment causing trim divided by MCTC. This is always the formula, but this changes according to the problem. It sometimes becomes W into D by MCTC, where W is the weight added at a point D from the center of flotation. It could be W that is shifted a distance D inside the ship itself from one point to another. We have done, that's what. So, depending on the problem, that moment causing trim will change, but as long as you know what it is, it's okay. You just have to find the moment anyway. So, W into D by MCTC. In this case, it becomes P into L by MCTC. In fact, this is the only 3 types of problems are there. One is when a weight is added at some point, that point at which it is added, the distance from the center of flotation becomes D and W is the weight added. If it is removed, then it's bodily rise, it's just minus. Then the other possibility is a ballast or some fuel, will say, is moved from one point, let us say compartment 1 to some compartment 3, from the aft of the ship to the forward of the ship, like that. There the weight of the ballast moved is W and the distance through which it is moved is D, that is W into D always. The third possibility is this P into L. When this P force comes, the reaction force from the ground comes. So, you have P into L. L is again the distance between the aft perpendicular and the center of flotation. So, this you find the change of trim, and then once you find the change of trim, you find the change of trim aft, find the change of trim forward. So, you find these 2 things. Now, aft is given by small l by capital L into total T, like that. Then okay. Then final draft will be this bodily sinkage plus this change. Okay. The initial trim, you know, it is given, draft is this your the initial not trim, initial drafts are given, draft plus bodily sinkage plus or minus bodily sinkage plus or minus the trim, and yeah, that's all. That's how you find the final draft of the ship if it is asked. Okay, then okay, that is this problem. Then now one problem is possible, which is, it's also same, it's just slightly different. That is, it's like this. That is, in this problem, instead of the ship coming and hitting at the aft perpendicular, due to some damage condition, the ship comes and hits somewhere in the middle. Okay. So, that is the only difference in the problem. So, it does not dry dock at the aft perpendicular, but it dry docks at the some point in between, and so the only difference becomes that that taking the distance from the center of flotation to find the moment, it is now no longer the distance to the aft perpendicular, it is the distance to that particular. In fact, that is the only difference. We will just do it, but that is the only difference. So, the problem is this. So, a vessel has been damaged forward and now it is going to be docked in the following condition. Anyway, taking into account the effect of damage. Now, you are told that waterline intersects the forward perpendicular at 10.2 meters. It means that the draft forward is 10.2 meters and the draft aft is 9 meters. As you can see, this is a damage condition. The draft forward in this case is greater than the aft. So, that's what, it's not a normal condition. In general condition, you don't see like that. Always you will see the aft more than the forward. So, because of this condition, while you are trying to dry dock it, it hit the it says vessel touches the blocks 10 meter after forward perpendicular. So, actually it hit the front part, not even the aft, it came and hit like this, it hit here first. Okay. So, that is the vessel touches the blocks 10 meter after forward perpendicular. Then the hydrostatic some data are given Km0, Kg0, MCTC, TPC, LCF, length, displacement. Now, you are asked the final GM when the ship hits. So, as you can see, the only difference in this problem, I am pretty sure you would have done this even if I didn't done this, because that is the only change, the only. So, you have to find an LB, the new distance LB, which will be the distance between the center of flotation and the point at which the ship hits the block. So, in this case, some let us see, you are given that LCF is 84 meter forward of aft perpendicular. Actually, distances are given in this case from the forward perpendicular, means vessel is touched. So, you need the length. So, it will become like this, length 176 minus the let us see, minus 84 will take you to the LCF, minus 10 will give you the distance between LCF and the what is this? This is equal to 82. Now, this is the distance between your center of flotation and your point where the ship hits. Now, therefore, your trim in this case becomes P into this LB divided by MCTC. Okay. So, you get your P, which is equal to your trim into MCTC divided by LB. So, you just do this, you will get your trim, it comes to 643.9 tons, comes to this. Then the same, you can do it two ways, you can either calculate it G0 G1 or you can calculate your M0 M1, whichever way. In this case, if you do it this way, M0 M1 can be taken as P into Km0 divided by W, which is equal to your here 643 points, which is 654 into Km0 is given to be 11.25 divided by W, the displacement of the ship 35,500 tons. Okay. So, this will give you your G0 M, this will give you your M0 M1, and you are given your initial GM, I believe you are given Km and Kg. So, you know, even though you do not need the initial portions of the course to do the last portions, but I do not think you can do any of these without remembering the previous things. Okay, because everything, like if I ask you what is, in the previous problem we did, like what is the writing moment at 1 degree heel, you have to remember that it is delta into Gz, where delta into Gm sin phi. So, most of the important formulas are throughout the course, that has to be remembered, and what is TPC, what is MCTC, that and all we did long back. So, all those things, all these formulas have to be remembered, and even that is what, when you are reviewing these things, also touch upon things like coefficients, block coefficient, prismatic coefficient, all, because in this problem instead of giving things like displacement, I might the problem might be just give CB, just to make sure you remember something from the previous section. Okay. So, you should also know that is what, all these important formulas should be remembered always, plus the block coefficients, all those. And okay, then GM. So, in this case you have your G0 M0 is given as Km0 minus Kg0, this you can calculate, and your final G1 M0 becomes G0 M0 minus G0 M0 minus what did we get, M0 M1. Okay. There is a decrease in GM, this will give you 0.446 meter. So, this is your new GM, your G0 M0 was 0.65. In case you are confused whether to add or subtract, please remember that dry docking will only decrease the stability, it will never increase the stability. That means, your GM should never increase. Okay. So, if you do not remember the figure that G went up or M came down, whether it is going up or down, At any rate, you should make sure that the stability only decreases during dry docking. If you remember that, you know that GM can only decrease, and as it keeps decreasing, and when it becomes 0, it becomes unstable. Okay, so this will give you, and the same thing, if you are asked the final drafts, same thing, trim, you find the change, trim aft, trim forward, in this case bodily sinkage, then you, I think it's a bodily rise. See, in this case, remember, it's not a bodily sinkage, because this P is actually up. Okay, when it comes up, it is up, so it's going to be a bodily rise, not a bodily sinkage. Actually, in that previous problem also, when you are doing P by TPC plus that, P by TPC will become negative. Let me see, yeah, it's subtracted. So you have to just remember that please remember, P, this is a bodily rise in this problem in dry docking and not sinkage. Okay, so this kind of covers the section on dry docking. So one small thing associated with dry docking is a phenomenon which we call as grounding. Grounding is like an accidental dry docking, means suppose that a ship is going in some shallow water, and you must have heard, not tides, you know what is, okay, suppose suddenly the tide falls, means the water level suddenly falls because of the tide change, and the ship might end up hitting some rock below, and means it will just come down and hit some point, so you don't know what that point it is, so that it's like an accidental dry docking. Okay, so it comes and hits there, and it's damage, it causes damage to the ship, and that phenomenon of it's really a phenomenon associated with damage of the ship, that's called as grounding. But grounding is used in many ways also. In case a ship is damaged due to anything, any process, you call it grounding, but really the word grounding stands for this process. When it comes down, hits some point, in fact you will see a lot of, if you just look at the internet itself, like news, you will see all the time, ship grounded near the some harbor, ship grounded near the coast, like that. The meaning is this, grounded means it's damaged and it's stuck somewhere. So I'll just, the definition I have just put here, you can just read it. Ship grounding is a type of marine accident that involves the impact of a ship on the seabed, damage on the, which causes damage on the hull and on the bottom structure. So it can cause damage, and it can affect the ship's stability and integrity, structural soundness, it will affect that. So the ship is no longer safe to be used, and the reason is because it's such a heavy load suddenly comes on some point of the structure, it causes structural damage. I mean, you are doing marine construction and building, you'll have some idea of what will happen if something suddenly strikes. So this is the grounding. Now this has now let us suppose that here that equation, what it says is that change of draft at C, I have written. C is actually, by C we mean the point where the ship hits the point, ship hits the ground, that point is called C. Now at that point, the change in draft at C will be, I mean, that is a common formula, change of draft anywhere is given by this formula only, change of trim at C plus that. Now in this particular case, see, in that the only thing which looks new here is that x. Okay, this y is the change of draft at that point C, and x is the distance of that point from the center of flotation. So like we did the previous problem, we saw what happens when the ship grounds at a point, ship dry docks at a point which is not at the aft perpendicular. So the same thing, that x is the distance from the center of flotation to the point to C, means C is the point where it hits the ground or the whatever rock or something. So this is the expression for the change of draft at C. Now this problem will explain, that is, you can have see, suppose you have a vessel floating at draft forward 8.7 meter, aft 9.4 meter. it suddenly grounds at a point 30 meter aft of the forward perpendicular, and estimate the draft. So, the thing is here, see, estimate the draft of the vessel after the tide has fallen by 70 meter. What has happened is it has grounded due to some reason, and then the tide is falling by 70 meter. The only thing you need to know here is, see, even though the tide has fallen by 70 meter, you say, you cannot say what is the change of draft at any point on the ship other than at that point where it is grounded. You see why that is? Because the ship is like this. Now, if the water level falls, it can go here up or down like this. Therefore, you really cannot say what is the change of draft at any of these points. I mean, this point, but this point you can say. Here it cannot go up or down. Therefore, if the water level falls by 70 centimeters, the change of draft at this point, you know, it can only be 70 centimeters, but at any other point you cannot say. You can calculate it using our formulas and all that, change of trim, change of using those formulas, but you cannot say directly it's 70 meter, it is not 70 centimeters. Okay. It's like that previous problem again, you have to know slightly that the water level, how it changes. Okay, that's the only thing.
So, it will be initial draft minus this 70 meter when it touches the
at the sea, at sea, yes, at sea it will be initial draft minus 70 centimeters exactly. So, but it is not true at any other point. At any other point you have to consider the trim into account. Okay, and so that's all. The problem is actually the same as the previous problem. Now, in this case you are told that, so what do we know? We are told that the draft of the vessel, we know that the change in the draft of the vessel at sea, okay, change in the draft of the vessel at sea is 70 centimeter. We know that, that is given because the tide has fallen by 70 centimeters. So, change in draft at sea is 70 centimeter, and the change in draft at sea is given by the formula. The change in draft at sea is given by the formula bodily sinkage, bodily rise in this case, bodily rise plus, so so this will be negative plus this thing, change of trim at sea. Okay. Now, change of draft at sea is given in this problem 70 centimeter, that is equal to bodily rise, which will be given by P divided by, we do not know P here, means we do not know what is the reaction from the ground here. So, P by TPC, TPC is known for the ship, it is given from the problem, and plus change of trim. The only point is that we need to know where it is grounded. Okay, that is given in the problem. The ship is grounded at a position 30 meter aft of the forward perpendicular. So, that is given. So, you know what is x. Okay, x is the distance between the center of flotation and the point where it is grounded. So, x divided by L. So, this is actually at that point, change of draft at that x divided into total trim. Total trim is given by P into x divided by MCTC. So, that is all. So, here we know x, we know the length of the ship, we know MCTC, we know TPC. Therefore, your only problem comes to finding P. Okay. Therefore, we know now the reaction force from the grounding at the point C due to this grounding, and once you know P, we can find the change in GM by using the formula G0 G1 is equal to, what was it, P into Kg0 divided by W minus P. So, this formula will give you G0 G1 which is the change in GM. Now, from this you know G0 M0, this we get from your previous expression Km0 minus Kg0. So, you get same formula G0 M0 minus G0 G1 will give you your G1 M0. So, you know your final GM. Now, so in this such a problem, you the only two things they will be interested in, one will be to find the GM that you have already calculated, the other will be to find the final drafts aft and forward. You know the draft at the sea, okay. You need to find the draft aft and forward because of this. Okay. So, So, that is very simple again. You know what is the trim P into x by MCTC. You can find the change of trim aft L by small l by capital L into that trim T, that will give you your change of trim aft. Then similarly you can find the change of trim forward, then you find the bodily sinkage or bodily rise. So, the initial you are told that it is floating at draft forward and aft. So, you know the initial drafts. So, initial draft plus bodily sinkage, or in this case it will be minus. So, the bodily rise plus the final trim, that is all. So, this will give you this problem of grounding. Okay. So, this is so we have more or less covered the section on dry docking and grounding. Grounding is dry docking only, except that dry docking is done by us and grounding is an accidental process, and dry docking is always done at the aft perpendicular if the ship is not damaged at any. So, when a ship comes, I mean the people will be able to say, we will know if whether it is damaged or not. Most likely it might be damaged, but if it is not heavily damaged, it will be floating by the, it will be like the stern side will be down and the forward side will be up in most cases. So, once you have that, when the water level comes down, most likely the aft perpendicular will touch the ground, unless it is heavily damaged and it is like this in the as in the other problem, then of course some other point will hit and it can be dry docked like that. So, this is the whole process of dry docking, and now we will go into the next chapter. This is two words. This, I mean, it's there are two names used to describe this process. One is called as flooding or damaged. Actually, there are three words to describe the process. One is flooding is the word. You call it damaged. This is the new chapter. Okay, I am starting the new chapter. So, chapters, it's okay, that it's described either as, because there are two books I am following right now. One is this Behrend's book and the other is that other book. Now, one book, the first book calls it flooding, this book calls it bilging. Both are the same process. Some books call it damaged stability calculations, that is also the same thing. So, same thing is described as flooding processes. In when you study hydrostatics and stability, any book on that, you will see it described either as flooding process or as damaged stability calculations or as bilging calculations. So, three things represent the same thing, all of which the meaning is this, as the the screen says, that is let an empty, this is as described by Solas. I do not know if you have, I think I have said it actually stands for Solas means safety of life at sea, that is Solas. Oh, you have done in marine construction, there you have done a lot more. Yeah, that maybe you have seen that. See, there is something called as Solas, safety of life at sea. They have that's a convention, actually started after the Titanic disaster. So, that is when they started, 1915 or something they started, and in London, and now it's a big regulatory body. It is called the International Convention of Safety of Life at Sea. Now, what they say about flooding is like this: let an empty compartment be holed well below the water line to such an extent that water may flow freely into and out of the compartment. A vessel holed in this way is said to be bilged. So, as the name itself suggests, you have a big vessel, okay, and let us say that it is divided into some 5 compartments, and suddenly some compartment, either at the end somewhere it is developed a hole in it, and that compartment is partially or fully filled with water, and so that is why we call it flooding. So, it is flooded with water, and now we calculate, just because one section is holed, that does not mean the ship has to sink, there is no such thing, okay, but because see the compartments, you know that they are watertight, they will prevent water from entering it, unless it is a very heavy break, it is unlike like the Titanic or something, it is not going to sink as such. So, this will cause damage and water let it keep coming in. Now what we do is we do the calculations, damage stability calculations, and see what is the stability of the ship in such a condition, and we go as far as checking to see how many compartments can be hold before the ship sinks actually totally. So this is the whole concept as in this chapter. Okay, now some important things that is needed. Okay, this I'll come to this later. That is okay. Now before we go into the processes of doing the let's wait. This can wait for the time being. That is before we go into the we need to know some terms. The first thing is the first term is okay, bulkhead. You know what is bulkhead, you have done bulkheads. These are the, we can call it compartment, it is what separates them, compartments. Bulkheads are there. Then there is a word that we one word that we use is the floodable length. As the name itself suggests, floodable length means that it is the total length of the ship that can be flooded without the ship sinking. Okay, that is the definition for floodable length. That is what it means. Now, also let us define something like this.
So exactly which length will it depend upon that?
Length, not breadth, length. Length of the ship, total length of the ship that can be flooded. So we are looking at it, if you are looking at the, I mean if you have the total length of the ship like this, then and it is divided into compartments, we are seeing the total length that can be flooded or that can be broken, or amount of damage that can be
But flooding the compartment 1 and 2 will be different from flooding 2 and 3.
Well, yes, that is true actually. Well, it is defined as the maximum length that can be flooded. Okay, so let us see which, yes, it is the maximum length that can be, it is true. If it is flooded here, it will be different from what is flooded here, that is true. So it is the maximum length that can be flooded, which that means you basically are taking the safest region, that so that will be where you have the maximum length. The more crucial regions you can have only lesser length, that is true. So it is the maximum length that can be flooded. So there is now another thing, now now suppose the ship is flooded by some method, the water line up to which the ship can go up without any I mean it can go up safely, the maximum water line up to which it can go up safely is known as a margin line, somewhere here. So the maximum height up to which it can go up, this is the means the water line can come up to here, and without the ship completely sinking, that this line therefore is known as a margin line. Okay. Now another term that is used is this we need floodable length, and one more thing is a word called permeability. The word is used in many contexts. In this, even in naval architecture, it is used many places. Permeability, and in this particular, the meaning is suppose that you have a compartment which has a volume V. You know that there will be different things in the compartment. Therefore, the amount of floodable volume is never V. It is always less than V. Okay, some volume less than V. Therefore, we say that the ratio of the floodable length to the actual volume of the compartment is called as permeability. So, the floodable length, let us call it as Vf. So, V is the total volume of the compartment. This will include things, different things are kept, like there will be different kinds of constructions in the room. So, that will reduce the floodable length. So, this ratio is a word called permeability. In general, and the word is mu, and the usually when we talk about permeability, we are talking about volume permeability. Though of course, there are times when when you read the literature, you will see surface permeability also, means you are talking about surface area in that case, but mainly we talk about only volume permeability, means the total volume that we cannot be using, means the total volume that we will not use for flooding. Okay, then now this problem, now we will go into the calculation of the damage stability. Now, this calculation of damage stability, there are two main methods in which you can do it. Please remember these two methods, because I mean at least the name itself, if you remember, you will get an idea of how to do that problem, and that name is very important. At least the name should be very important, because people keep talking about it. This is an important section, like if any of you take up a job in shipyard or anything, this is an important section, because you will always be coming across damage, in fact that is what shipyards do most of the time. You are not going to be building ships all the time, you will be repairing ships only, it will be like damaged ships keep coming. And so what you do is, you need to know this damage stability calculations, two methods, they are very famous and in this section. And so these two methods are usually defined as method of lost buoyancy. So, I am repeating, please remember these two names, and method of added weight. These are two ways in which you can calculate damage stability or flooding. Now, okay, now when a ship, first of all you have the ship, suppose that some section is now damaged or some compartment is damaged. So, what happens? Water has entered into the compartment. Now, initially what do we have? We have some weight of the ship, something inside the ship, lot of items inside the ship, and this weight acts down, and the volume, okay, the volume itself produces a buoyancy force upwards. Okay, that is how it is usually. Now, what happens? Now, water has entered such that inside that the weight of water and the volume of that compartment gets cancelled out each other. Okay. Now, there are two ways in which we can solve this problem. When you have a ship, what we can do is that, see in that section the weight and the buoyancy are cancelled out each other. So, what you do is, you assume that in the method of lost buoyancy, this is the first method, the other method we will describe later. Method of lost buoyancy, we assume that that section is really not a part of the ship anymore. Okay. So, when you do that, so because initially that was a part of the ship and there was a buoyancy from that, now water is there, that water balanced the weight of the buoyancy from that section, therefore, it is like that is no longer there, you can neglect it, the totals, that region is removed completely. So, the ship is now without that compartment, that is how you do proceed with the calculations. So, some things we can directly read, this is the method of lost buoyancy. You can say that the flooded compartment does not supply buoyancy. So, this is directly it, means there is that part, that is not part of the ship anymore. But one, remember, the weight of the structures in the ship does not change, that buoyancy is lost, that is all, and weight of water is lost, means the weight of the water that is entered is cancelling the buoyancy, whatever is there in the ship is there, that means the weight is not, is it clear? Because this should be clear. What has happened is, the ship is as such, there is no change, water has entered, water is cancelled out the buoyancy, therefore, there is no more buoyancy of that part, water is an additional thing, but whatever weight is there inside, it remains as such. The ship is not changed, nothing is changed except that buoyancy from that section is lost. So, that is what it is. So, what it says is that, so the flooded compartment does not supply buoyancy. Now, you can see that weight of the structures is still part of the displacement of the ship. Okay. Then as I will go to D, which that is that once you have, so since the weight of the ship or the position of anything in the ship has not changed, what has happened is displacement remains same, displacement of the ship is the same, and center of gravity has not changed, because none of the items in the ship we are changing. So, I mean this is in very nutshell I am putting the whole concept of whole concept of loss buoyancy and added weight. If you want, you can take this down, because it is not written this clearly in the book. Just these are the important points of loss buoyancy and added weight. Okay. So, this, and then since we assume that that compartment is no longer a part of the ship, that water that has entered is also not a part of the ship. So, water is also not a part of the ship, and buoyancy is not a part of the ship, that much have cancelled out, that is not a part of the ship. Therefore, there is no such concept of free surface effect. Okay. Free surface effect is due to the, free surface effect means due to the water that has entered that compartment. Remember, when water enters the compartment, some section will be, you know what is free surface, that free surface will come, and when it goes slants up, it will produce some change. Now, when you, yes, and when you, since this part is not considered part of the ship and that water is also not part of the ship, free surface effect does not come into this calculations. And now the so this is more or less the main points of added buoyancy. Actually, when you will do some, when we do some problems and when we describe things detail, it will become very clear, because there always is a slight confusion in this. But it is very straightforward really. And so, this is the method of loss buoyancy. We can just therefore, let us look at this, that is, what we can say is that delta final, which is the final displacement, is equal to one minute. Oh, sorry, this is added weight, because I made it, because the displacement does not change in this. So, I have not explained added weight still. We will just do the loss buoyancy right now. Now, now okay, let us do this. So, initially we have delta 1, delta initial, del initial is your, we will do one thing, let us take a very simple case like a box. Let us take a box like this, and let us divide it into 3 compartments, compartment 1, compartment 2 and compartment 3. Let us suppose it has a draft of T initial, T I stands for T initial, then it becomes, okay, T initial first, then now let us assume that this middle compartment gets flooded. So, C2 is okay, this has a length L and it has a breadth B. Things actually become much more simple when you do these box shaped things. We can just like I, all those things we can calculate very easily. So, we use this for the time being. So, we have length, breadth and draft T I. So, the initial displacement of the ship is given by L B T I, okay, which is L, whatever you have your L B T I, and your displacement the mass displacement or weight displacement is equal to rho into del I. This will give you your, you can call it delta I. This is the weight of the ship. Now, this is before the ship has flooded. Okay, we are doing it two ways. Same thing, I will do it finally once the ship has flooded with method of, we are doing the method of loss buoyancy. Okay, method of loss buoyancy. So, first we will just we will just describe the steps. You know all these steps, but still I will do this. So, delta I is known. Now, I, suppose I need to calculate the moment of inertia about the center line. I is defined as I initial is equal to b cube L by 12, okay, and the initial metacentric radius Bm initial is equal to I initial divided by del initial. So, it is I mean you know this because it is a box shaped barge, it should be b square by 12 t I. So, this will become Bm, this will give you your Bm initial, and position of your center of buoyancy initially will be Ti by 2. Now, your Gm initially will be Kb initially plus Bm minus Kg. This will give you your initial Gm, which will Kb is T by 2, T is the draft, T by 2 will give you your Kb, Bm is got by I by del, that will give you your I Bm, and Kg will be Kg in this case is just a half. If we have not given the depth, no, well, I think the depth is also given probably. Yes, depth is also given, and therefore, Kg, well actually they haven't written, but Kg is, it is the half, it is somewhere in between, exactly in between. Now, one more thing I will just we need to know here is the writing moment in this condition, the writing moment is given by Mr equals delta initial into Gz, okay, which is equal to delta initial into Gm sin phi or Gm initial sin phi. So, this will give you your initial writing moment. Now, our next purpose is, once you consider the method of loss buoyancy, what will be your all these things. You start from del, actually that I have already said del is the same, we are not changing the, we are not assuming that the weight of the ship has changed. So, delta is same, then I will change, we will see that. That is, we have already said the, now the next problem is when this region is flooded, okay, this region is flooded, means we assume this much is flooded, and then we do the problem and see what are the final all these things. Finally, we have to find the writing moment in the case when we have to find Gm, and then finally the writing moment when the ship is flooded in one of the compartments. Now, after we finish this method of loss buoyancy, I'll start with the method of added weight, and then we will see that both these methods yield exactly the same result. It's whatever you are doing, it's the same thing you are doing. So, the same result you will get. Okay, now I think I'll stop here. The next section is little long, we will do it in the next class.